we all know that taste is one of the five senses we use to experience the world around us. Receptors on the tongue are very sensitive to chemical stimuli that lead to five basic taste sensations. And these are the sweet, the sour, the salty, bitter, and the umami. By the way, the umami word comes from the Japanese word meaning delicious. Now, the sensation of sour responds to the presence of acids. No? Acids and bases are important in numerous chemical processes around us. And as we get to the end part of this subject, we get to be introduced to acid-base chemistry, which is involved in a lot of equilibrium processes. Now, to theoretically define acids and bases, acids on its theoretical definition is defined as chemical compounds that show in a solution a sharp taste, a corrosive action on metals, and the ability to turn certain blue dyes to red. While bases, on the other hand, are chemical compounds that in solution are soapy to touch and turn red dyes to blue. Now, when mixed together, acid and base neutralize one another, then as a result, it will produce salt. Salt is a substance that has a salty taste, but none of the characteristic or properties of either acids or bases. Now, for the properties of acids and bases, we get to see the difference. No? For the acid, it has a sour taste with pH of less than 7. With litmus paper, it will turn to red. And when phenolphthalein is being used as color indicator, it will remain to be clear. While for the base, it has a bitter taste, slippery or foamy to touch, with pH greater than 7, and with the litmus paper, it will turn to blue. When phenolphthalein is being used as color indicator, it will turn to pink. Now, we already have the theoretical definition of acids and bases. At this point in time, we'll look at the Arrhenius definition of acids and bases. So Arrhenius definition was developed by none other than Svante Arrhenius. It says that an acid is a substance that, when dissolved in water, increases the concentration of hydrogen or hydronium ions, while base is a substance that, when dissolved in water, increases the concentration of hydroxide ions. In this definition, we must take note that a substance to be considered acid, it must increase the concentration of hydrogen or hydrogen ions. While for the base, for the substance to be considered a base, it must increase the concentration of hydroxide ions. Now, let's go to the next definition of acids and bases, the Bronsted-Lowry acids and bases. Bronsted or The definition of Bronsted-Lowry acids and bases was independently developed both at the same time by Johannes Bronsted and Thomas Lowry. It says that an acid is a species having a tendency to lose a proton, and a base is a species having a tendency to gain a proton. So, in simple explanation, an acid is a proton donor and the base is a proton acceptor. The term proton here that we are trying to define or we're trying to discuss means the species or the atom hydrogen. Okay, the H plus or the hydrogen. This in this picture, a Bronsted-Lowry acid in the form of hydrochloric acid or the HCl must have at least one removable acidic proton in the form of hydrogen that can be donated to our base, wherein a Bronsted-Lowry base must have at least one bonding pair of electrons to be able to accept a proton. Now, to explain further what is Bronsted-Lowry acids and bases, we have here an example that uses hydrochloride to be dissolved in water. When hydrochloride dissolves in water, we will able to come up with an equation with this. HCl plus H2O will result to Cl negative plus H3O. Now, the hydrogen in HCl, as you can see, gets to be donated to the base, which is the H2O or the water. And as a result, it will produce chloride, which is the Cl negative, and then the H2O, which is the base, will now become the H3O. H2O to H3O, since it is the one who accepts the hydrogen being donated by the HCl or the acid. At this point, I want you to be familiar with some vocabularies that are absolutely essential in this discussion. So for the acid-base equilibrium reaction like this one, right? As you can see, the reaction that loses an H positive or hydrogen atom is called the acid, based on the definition given to us by Bronsted and Laurie. It is the HCl in this case. And the reactant that accepts the hydrogen atom is called the base. In this case, it is the H2O or the water. Now, the product that arises from the acid is called the acid's conjugate base. And in this case, it is the Cl negative. And the product that arises from the base is called the base conjugate acid. And in this example, we have the H3O. Confused? Now let me explain it further. Once again, all right, in this reaction, we have to look at the left side of the equation. And the left side of the equation is composed of hydrochloride and H2O. Now, identify one of these two is the acid and identify one which is the base. So in this equation, as what I've said, our acid is the HCl since it is the one who was given off or was taken off the hydrogen. And our base is going to be the HCl since it is the one who accepted the hydrogen from the acid. Now, as we remove the hydrogen from HCl, the thing that's left over is the Cl. And this Cl will now go over to the right side of the equation and it will become Cl negative or chloride. It is the product that comes from the acid, making it the acid's conjugate base. Now, the thing that emerged from our base is the hydronium, which is the H3O. This H3O is the product formed when the water right here from the left side of the equation accepted the hydrogen from the hydrochloride, and it will now be considered as the base conjugate acid, making it the H3O. Now, let us look at another example. In this equation, we have nitrous acid reacting with water or HNO2 reacting with the H2O. What we do is we look at the left side of the equation. Focusing on the left side of the equation first makes it very easy to identify which is our acid and which is our base. Now, the acid is the thing, again, that gives up hydrogen as it moves over to the other side of the equation. In this case, that's definitely the nitrous acid. Nitrous acid or the HNO2. The nitrous acid gives up hydrogen and transfer it to the water, which is our base, the H2O. And the HNO2 here will now become NO2 negative, given that it is already here on the right side of the equation. And the water, who's the one who accepted the hydrogen, will now become H3O. So from H2O, it became H3O positive. And that will be the base conjugate acid. And the NO2 right here is our acid's conjugate base. Now, water doesn't always act as a base. In this example, we can see something different. Now, in this equation, let's try to identify which thing is giving up the hydrogen. So let's look at the equation from left to right. You can notice that the water is the one that giving up the hydrogen. That's what you can observe. And the NH3 is the one that accepts the hydrogen. Now, meaning to say, the water, since in this equation, the water is the one that gives off the hydrogen, it is considered to be our acid. And the NH3 right here is the one that accepts the hydrogen, meaning it is considered as the base. As a result, the NH3 became NH4 and the H2O became OH negative. So again, now in this equation, water doesn't always act as a base. Now, how do we know or how can we figure out what a conjugate acid and what conjugate bases are? Now, first again, no, to be able to come up with a conjugate base and a conjugate acid, we must figure out which is the acid and we must figure out which is the base. Again, by definition of Bronsted and Lowry, acid is the one that lost the proton, while base is the one that receives that proton. Now, to be able to figure out what is the conjugate acid or and conjugate base, to figure out which is the conjugate base, it is a product that looks exactly like the acid but with a negative charge replacing the hydrogen. To be able to figure out which is the conjugate acid, we must take note that it is the product that looks exactly like the base but with an hydrogen and a positive charge added to it. Now again, to make a conjugate base, we just have to remove an H from and add a negative charge to the acid. While to make a conjugate acid from your base, we just have to add an H and positive charge to your base. Now, I hope it already makes sense to you. Now let's try the following example. We have here acid and conjugate base. So for the acid, we have the acetic acid. By the way, acetic acid is found in the vinegar. For the acetic acid, it is composed of CH3, CO2H. Now, as explained, no, we have to take off the hydrogen in the acetic acid and replace it with a negative charge. So as a result, we now have a conjugate base of acetate or CH3CO2 negative. As you can see, no, the H on the acetic acid has already been removed and was replaced with a negative charge, giving us a product or a result of acetate with a composition of CH3CO2 negative. Now, another example is we have the hydrochloric acid. No? We've already mentioned hydrochloric acid from our previous example kanina. Once again, we remove the hydrogen from the hydrochloric acid and replace it with a negative charge, giving us a product or a conjugate base of chloride, which is Cl negative. Okay. Now, in an aqueous solution, our aqueous solution can either be acidic, basic, or neutral. How would we know? Now, if a solution is acidic, hydrogen ion concentration is greater than the hydroxide ion concentration. While if the solution is basic, hydrogen ion concentration is less than hydroxide ion concentration. And we will know if the solution is neutral if the hydrogen ion concentration is equal to the hydroxide ion concentration. Now, these three equations will give us an idea whether a solution is acidic, basic, or neutral. Now, let's proceed to our next topic, which is the storage cell and galvanic cell. Now, a storage cell, or what we call the battery, is a galvanic cell or a series of galvanic cells, which contains all the reactants needed to produce electricity. Batteries, as we all know it, are cleverly engineered devices that are based on the same fundamental laws as galvanic cells. The cell and battery both store the chemical energy and then transforms the stored chemical energy into an electrical energy. Now, we will focus on what is a galvanic cell. Now, the use and importance of cells and batteries are unquestionable. We all know that because in our day-to-day lives, we make use of cells or batteries in so many different ways. And among other cells, a galvanic cell is a type of electrochemical cell that is defined as an acts as a device in which simultaneous oxidation and reduction reactions take place. These reactions are used to convert the chemical energy into electrical energy which can be utilized for any commercial purposes. Meaning to say, it is used to supply electric current by making the transfer of electrons through a redox reaction. And of course, the engineers or the chemist who was able to develop the galvanic cell, no, it is an exemplary idea of how energy can be harnessed using simple reactions between given elements. Now, how does a galvanic cell works? So I have here a picture that shows how a galvanic cell works. Now, the working of a galvanic cell is quite simple. It only involves chemical reaction that makes the electric energy available as its end result. Now, during a redox reaction, a galvanic cell utilizes the energy transfer between electrons to convert chemical energy into electrical energy. And the cell includes two electrodes. One of these electrodes is the cathode, which is the positively charged electrode, while the other is the anode, which is the negatively charged electrode. These two electrodes, the anode and the cathode, shall form the two essential components of the galvanic cell. The chemical reaction related to reduction takes place in the cathode, while the chemical reaction related to the oxidation shall take place in the anode. And it has already been said, any two metals can be used to create chemical reaction. Now, in this example, to be able to furtherly explain what is or how the galvanic cell works, we're going to use two elements, the zinc sulfate and the copper sulfate. Now, as the chemical reaction takes place, the zinc right here, the zinc right here would end up losing two electrons. This will be taken up by the copper to become elemental copper. And since these two metals will be placed in two separate containers and would be connected by a conducting wire, an electric current would be formed, which would transfer all the electrons from one metal to the other. At the same time, the two metals shall be immersed in a salt solution. Let's say, for example, in this picture, we have the zinc sulfate and copper sulfate. The two solutions are not mixed together directly, but it can be joined using a bridge or what we call the medium. In this example, we have the salt bridge, and this salt bridge is the medium that shall be responsible for the transfer of ions, but also make it sure that the two solutions does not in contact to each other. Such bridge or such medium can help in completing the circuit for carrying the electric charge and also makes it sure that the solutions in the container will remain neutral. The galvanic cell, as what I've said, utilizes its ability to separate the flow of electrons in the process of oxidation and reduction and connecting each with a wire so that a path can be formed for the flow of electrons. This flow of electrons is essentially called the current, and this current can be made to flow through a wire to complete a circuit and obtain our aim or the output of a galvanic cell, which is the electricity. Okay, so I hope you've learned a lot from our topic today. And that would be all. If you have any questions, um, you may email me or you may send me a message through Hangout. Thank you very much for listening.